Hello and welcome back. In the last three videos, I talked about carbonyl compounds. In this video and the video following this, I will be talking about carboxylic acids. In this video, we will see nomenclature and structure of carboxyl groups at first. Then we will see some methods of preparing these carboxylic acids, and at the last, we will see some physical properties of carboxylic acids. So let's do a quick revision now. Carbon compounds containing a carboxyl functional group, that is COOH, are called carboxylic acids. The carboxyl group consists of a carbonyl group, that is CO, attached to a hydroxyl group, that is OH, and hence we get the name carboxyl. Carboxylic acids may be aliphatic, COOH, or aromatic, like a benzene ring can be attached to COOH. Depending on the group, alkyl or aryl attached to carboxylic carbon. Now, let's look at the nomenclature, starting with common names. Since carboxylic acids are amongst the earliest organic compounds to be isolated from nature, a large of them are known by the common names. The common names end with suffix ic acid and have been derived from Latin or Greek names of the natural sources. For example, we know HCOOH is called formic acid and it was first obtained from red ants. Formica means ant in Latin. Similarly, we know acetic acid that is present in vinegar. Acetum means vinegar in Latin. Butyric acid similarly obtained from rancid butter, and butyrum means butter in Latin, and hence we get the name butyric acid for CH3, CH2, CH2, COOH. That's the common name. So we have seen the common names, and most of the common names are obtained from Latin or Greek names from the natural sources. So now let's learn something interesting, that is the IUPAC names. In IUPAC system, aliphatic carboxylic acids are named by replacing the ending E in the name of the corresponding alkane with oic acid. In numbering the carbon chain, the carboxylic carbon is numbered 1. So let's take an example. Let's try to name this compound over here. So we need to start from right. That is, the carbon of COOH should get number 1 and we move towards the left. So the numbering is like this, 1, 2 and 3. Hence, the name should be 2-methyl propanoic acid. The methyl group is attached to the second carbon. So we get 2-methyl prop because 3 carbon atoms in the main chain. So prop, and because it's an aliphatic group, and oic acid because it's a carboxylic acid. So 2-methyl propanoic acid. For naming compounds containing more than one carboxyl groups, the alkyl chain is numbered and the number of carboxyl groups are indicated by adding the multiplicative prefix like dicarboxylic acid, tricarboxylic acid, etc. to name of the parent alkyl chain. The position of COOH groups are indicated by the Arabic numerals before the multiplicative prefix. So let's look at some examples. Let's try to name this compound COOH, CH2, CH2, OOH. Here we have 2 carboxyl groups. So we can start the numbering like this 1, 2, 3, 4, 5. And there are 5 carbon atoms in the main chain. So pent, ane because it's an aliphatic group. There are 2 carboxyl groups, so dioic acid. So the name for this compound is pentane dioic acid. One more example. Let's try an aryl group now. This is a pretty simple one, so directly let's look at the answer. It's benzene 1,2 dicarboxylic acid. So benzene ring, and there are 2 COOH substitutions at 1 and 2 positions. So benzene 1,2 dicarboxylic acid. One more example. In this compound, the main chain is CH2COOH and the phenyl ring is treated as a substitution to the second carbon atom. Please note that. So we start numbering from the right because the COH group should get high priority 1, 2, 1 and 2, and the phenyl ring is substituted, so the name is 2-phenyl ethanoic acid. A familiar example, we have seen a similar thing in aldehydes. So here we have 3 COH groups and we need to give equal priorities to all of them. We can't say one of them should get a higher priority and others should get a lower priority. So to get rid of this problem, like in case of aldehydes, we saw that we took the main chain as a 3 carbon containing chain. So we number 1, 2 and 3. So prop is the root word which we are looking for. It's an aliphatic, so propane, and hence we get the name propane 1, 2, 3 tricarboxylic acid. So with this I would like to end this topic, that is nomenclature of carboxyl groups. Now let's look at the structure of carboxyl group. In carboxylic acids, the bond to the carboxyl carbon lie in one plane and are separated by about 120 degrees. The carboxylic carbon is less electrophilic than carbonyl carbon because of the possible resonance structure that is shown now. So these are the two possible resonance structures that we get. So that's with the structure, it's as simple as that. Now we will try to prepare some of these carboxylic acids. Starting from primary alcohols and aldehydes, then we will see from alkyl benzenes, then from nitriles and amides, from Grignard reagents, from alkyl halides, from aryl halides and anhydrides, from esters finally. So let's look at each of them now. First, preparing carboxylic acids from primary alcohols and aldehydes. Primary alcohols are readily oxidized to carboxylic acids with common oxidizing agents such as potassium permanganate in neutral acidic or alkaline media, or potassium dichromate and chromium trioxide in acidic media. The second one, that is K2Cr2O7 with CrO3 in an acidic medium, is called as Jones reagent. So RCH2OH, that's the primary alcohol that we have. When I treat it with alkaline K1O4 for example, followed by acidification, I get RCOOH, that is the carboxylic acid. This we have seen many times, I suppose. And similarly with Jones reagent, we again get RCH2OH gives RCOH. Carboxylic acids are also prepared from aldehydes by the use of mild oxidizing agents. Example, Tollens reagent, Fellings reagent, which you have seen in the while we discussed the chemical reactions of aldehydes and ketones. Next, from alkyl benzenes. Aromatic carboxylic acids can be prepared by vigorous oxidation of alkyl benzenes with chromic acid or acetic or alkaline potassium permanganate. The entire side chain is oxidized to carboxyl group irrespective of the length of the side chain. Primary and secondary alkyl groups are oxidized in this manner, while tertiary group is not affected. Suitably substituted alkenes are also oxidized to carboxylic acid with these oxidizing agents, which you have seen in Unit 13 of Class 11. For example, I have taken toluene. I am treating it with K1O4 KOH, so it's an alkaline medium. I get a carboxylate salt and I acidify it. I get the benzoic acid that I need. Now suppose I take this compound over here. What do you think will be the product when I do a similar reaction? Do remember that the entire side chain is oxidized to carboxyl group. So I will be getting a similar carboxylic acid salt over here, and when I acidify it, I get the benzoic acid that I need. Now from nitriles and amides. Nitriles are hydrolyzed to amides and then to acids in the presence of H plus or OH minus as catalyst. Mild reaction conditions are used to stop the reaction at amide states. So if I take an RCN, that is an cyanide, H plus or H minus H2O, I get RCO and H2, that's an amide. And if I continue this, I get RCOH. CH3CO and H2, similar reaction like we have seen this before, so I'm not going to explain this again. Let's move on. I can do it with aryl amide also, like C6H5CO and H2, a similar reaction, I get benzoic acid with ammonia. From Grignard reagents. Grignard reagents react with carbon dioxide to form salts of carboxylic acids, which in turn give corresponding carboxylic acids after acidification with mineral acid. For example, RMgX with CO2 in presence of dry ether, white dry ether, we have discussed this before. I get RCOOMgX, and followed by acidification, I get RCOH. Now we will see something interesting, that is from alkyl halides. As we know, Grignard reagents and nitriles can be prepared from alkyl halides. The previous two methods, that is preparation from nitriles and Grignard reagent, are useful for converting alkyl halides into corresponding carboxylic acids having one carbon atom more than that present in the alkyl halides. So, since we know how to prepare Grignard reagent and nitriles from alkyl halides, we can use the previous two methods, and note that in the resulting product we get one carbon atom more than the one present in the alkyl halide. So let's continue with from acyl halides and anhydrides now. Acid chlorides, when hydrolyzed with water, give carboxylic acids, or more readily hydrolyzed with aqueous base to give carboxylate ions, which on acidification provide corresponding carboxylic acids. So we have the reaction in chemistry, like in chemical terms, we have RCOCl. First with H2O, I get RCOH plus Cl minus. In basic medium, that is OH minus followed by H2O, I get RCO minus plus Cl minus with further H3O plus, that is an H plus. In fact, so I get RCOH. Anhydrides, on the other hand, are hydrolyzed to corresponding acids with water. So this is an anhydride, this is benzoic anhydride that I have taken. I am hydrolyzing it, I directly get 2 moles of benzoic acid. And similarly, benzoic ethanic anhydride, hydrolysis, benzoic acid and ethanoic acid. Now, preparation of carboxylic acids from ester. Acetic hydrolysis of esters give directly carboxylic acids. So ethyl benzoate, acetic hydrolysis, I get benzoic acid and ethanol. This reaction may be familiar to you. Basic hydrolysis gives carboxylates, which on acidification gives corresponding carboxylic acids. So now ethyl butanoate, that's the ester that I'm taking. I treat it with NaOH. I get CH3CH2CH2COONA plus C2H5OH. And when I treat it with H3O plus, that is acidification, I get butanoic acid. So with that we have finished preparations. Now we look at a small question and then we will move on to physical properties. So this is the problem to solve. Write chemical reactions to affect the following transformation. That is, we need to prepare benzyl alcohol to phenyl ethanoic acid and bromobenzene to benzoic acid. You can take 15 seconds. You can pause the video if you need more time. And yeah, I will discuss the answer after that. Okay, let's discuss the answer now. By the way, there can be many methods or many ways of preparing these compounds from a source. I will discuss only one of them. So for the first one, benzyl alcohol to phenyl ethanoic acid, I take C6H5CH2OH, that is benzyl alcohol. I treat it with HBr, and you will be expecting a C6H5CH2Br, that is a benzyl halide. Then I treat it with KCN, I get C6H5CH2CN, that's a cyanide, and followed by H3O plus and heat, I get C6H5CH2COOH, that is phenyl ethanoic acid. And in the second case, C6H5Br, I add Mg to it, I get C6H5MgBr, that is the Grignard reagent. We have seen just now that when I treat a Grignard reagent with carbon dioxide and followed by acidification, I get what I need, that is C6H5COOH. So I hope these two questions were clear. You got an idea how to solve such questions. Now let's move on to physical properties of carboxylic acids. Aliphatic carboxylic acids up to 9 carbon atoms are colorless liquids at room temperature with unpleasant odors. The higher acids are wax-like solids and are practically odorless due to the low volatility. Carboxylic acids are higher boiling liquids than aldehydes, ketones, and even alcohols of comparable molecular masses. This is due to more extensive association of carboxylic acid molecules to intermolecular hydrogen bonding. The hydrogen bonds are not broken completely even in the vapor phase. In fact, most carboxylic acids exist as dimer in the vapor phase or in the aprotic solvents. So this is the dimer state of carboxylic acid in vapor state or aprotic solvent. Simple aliphatic carboxylic acids having up to 4 carbon atoms are miscible in water due to formation of hydrogen bonds with water. So this is how the hydrogen bonds are formed in water. The solubility decreases with increasing number of carbon atoms. Higher carboxylic acids are practically insoluble in water due to the increased hydrophobic interaction of hydrocarbon part. What is hydrophobic? What is hydrophilic? Hydrophilic is water liking part, hydrophobic is water hating part. So it doesn't like water. So because of this increased hydrophobic interaction of hydrocarbon part, the higher carboxylic acids are practically insoluble in water. For example, benzoic acid, that is the simplest aromatic carboxylic acid, is nearly insoluble in cold water. Carboxylic acids are also soluble in less polar organic solvents like benzene, ether, alcohol, chloroform, etc. So with this, we have come to the end of this video. To summarize, we started off with nomenclature of carboxylic acids, then we saw the structure of carboxyl groups, then we went on to see some methods of preparing these carboxylic acids compounds, then finally we saw the physical properties of these carboxylic acid compounds. The next video, I will be talking about the chemical reactions and some of the uses of these carboxylic acid compounds. I hope the content in this video was clear, and I hope to see you in the next video. Goodbye.